So a couple of housekeeping things first. I know some of your CIAs and CMAPs just came out yesterday or the day before, and some of your scores are kind of wonky. What happened is some of the students who dropped out, like the Excel spreadsheet we used to keep track of these things got like messed up. So if you got like way too low a score, or if you got a 0 or something on your CMAPs and your CIAs or whatever, send Ali Hamza an email or a message or something, and we'll fix it. Right. So don't worry if your scores are a bit too low. Um, your exam 2 is on April 24th. Dr. S is going to tell you more about that later. It's not comprehensive. It's everything uh, uh, after exam 2. Everything we've done after exam 2. So that includes today's classes, and so that includes a priori, and that includes what I taught last week as well, cluster validity analysis. Your exam 2 results will be out soon. What's up?
What is the definitive date for the final? Is it 24th or the 28th?
For now, it's the 24th. If something changes, we will let you know. It's it's the 24th one. So for today's class, a priori, we will have an in-class assignment at the end of this, and the assignment essentially that you'll be doing in class is a very similar thing. It's going to be on your final exams as well. So make sure you understand what's going on. I'll in the final exam, the formulas and stuff will be there, but you should understand what's going on. And today's attendance, the access code is 2626. Today's attendance access code is 2626. So when you can, you should get on that. Okay. And the access, both the attendance should be up till the end of the class, till at least till 2:30, and the in-class assignment is going to be up till 6:30, preferably. So, okay, so if everyone's ready, we are going to start with a priority analysis, or let me see if this is recording. Yes. Okay. So a priori analysis, or an algorithm for association mining. Well, it sounds, what does a priori sound to? A priori means that like whatever has happened before affects something that has happened later, which is something that almost all recommender systems that you know of use in some way or the other. Modern recommender systems, whether it's Amazon or Netflix or Spotify or whatever you're using, they have far more complicated machine learning algorithms that they use for these purposes. But the fundamental principle that they follow is the a priori principle, which is whatever happens before affects whatever happens after. Now, the a priori principle that we are going to be talking about is called market basket analysis, which came out in around 93, 94. And this is the algorithm that they coined, the fast algorithm for mining associations. And what associations mean is that when someone in a database or in a transaction or in any live event, what event associates with a second event that happens after that. So if you're buying something from a store, what are you more likely to buy after that, right? So if you're buying seeds, are you also more likely to buy soil after that? If you're buying bathroom fittings, are you also more likely to buy towels? If you're buying portraits, are you also like landscape paintings or portraits or whatever? Are you also likely to buy hanging paints or paint colors or things like that? So again, these are not always obvious, and these recommender systems, even though they started with market basket analysis, where the big box market stores like Walmart or Costco or whatever, that is where all of these like a priori analysis rules and association mining rules started from. They're used everywhere online. Like they're used, a version of this is used in social media to control what you see on your For You pages on whatever social media you use. It is used by recommender systems in Spotify, on Netflix, on Hulu, on whatever you're watching. This principle has become like the fundamental core of any kind of recommendation systems. But the first where it originally started from is this pretty funny little image that Dr. Rizk created for us. It's the market basket analysis. So what is a market basket analysis? So it means that once you're at like Walmart or Costco, whatever, or HEB, and you're buying something, you are trying to analyze what people have bought and what they have bought previously to answer these questions. Like, who are the people who are making these purchases? So, your homework 4, for example, had a similar question at the core of it. Which items are customers buying together? So, like, which items are associated with each other? What is the order of purchasing? And when do and all of these things together tie together in time. So when do customers purchase the most, and what do they purchase when they're purchasing the most, right? So all these like small questions, they add up to one big question for these companies, is that how do they optimize profit? In what order should their aisles be? Which items should be the closest to their checkout location? Which items should be the furthest away from checkout location? So you arrange the entire big box store so that you maximize this profit motive. So you maximize the associations. So you take people through a logical chain. What items do they buy, and do they see this, and then they think of buying a second item, and they think of buying a third item, and what is the highest probability that you arrange these aisles and you arrange these stacks in such a way so that your company profits the most. Essentially, that is where it starts from, and there's a couple of terms that's going to occur over and over again as we talk about this. First is co-occurrence. Co-occurrence, as the name suggests, it means that when you are buying items, which items do you buy in a group, right? Like the example that I gave, if you're buying seeds, are you also buying pots? Are you also buying soil? Are you also buying mulch? Are these things are associated together, right? If you're purchasing one item of a salad, are you also purchasing the other items of salad? Are you purchasing Thousand Island branch associated with it? So those things need to be close together. Association rules is different from co-occurrence in that some people who buy an item, who buy a group of items, also buy a completely unrelated item. You don't have to know why they do this. In fact, a lot of these big box stores don't really, they employ psychologists to figure out why people who buy certain things together would also buy other things. But you don't need to know this. You just need to know the rules, right? That you are buying this group of items somehow indicates that you are also going to buy this another group of items. And sequential patterns tell you in what order do people usually buy these grouped up items, right? So if you, how this helps is that if you break the sequence in some way, you know that people might come back to the sequence in a little while longer. So if you want people to buy something, you put it in the middle of a known sequence. You put something attractive that people might buy at lower prices, at discount prices, in the middle of a sequence of items that you know that people are always going to buy together. Again, this is math, but this is kind of like psychology, right? You try to figure out how people work together. And even though it sounds very like abstract, these are very, very successful working patterns. Like there are billions and billions of dollars of profit in these patterns. And understanding and applying these patterns together, this kind of pattern analysis of customers, of implementation in big box stores, they're always hiring people who can do this well, right? So that's always something to keep in mind. But this is market basket analysis, right? But this is not where this kind of analysis stops. This kind of association mining Apriori analysis, it's not where it stops. Like I said, one of the biggest examples and the biggest use cases of this kind of analysis, and where all the breakthroughs, like all the modern breakthroughs in this kind of research come from Netflix. They come from Spotify. They come from all these big fan companies, these big tech companies who want to know what you're listening to or what you're watching, and how can that predict something else that you want to listen to, something else that you want to watch, right? There's a lot of money in this, so understanding these patterns are very critical. So let me give you a couple of examples of how this works on Spotify and how this works on Netflix. So this actually I screenshotted this yesterday. This is my own Spotify screen. So this Discover Weekly page and the other recommended Spotify recommended daily mix one, daily mix two, all these daily lists. This is one of the largest recommender systems in the world in terms of complexity. Now, this doesn't just use API analysis. I'll talk about what it uses, but understanding this, there are thousands of research papers figuring out how this works. Because if you can game this system, if you can understand how Spotify algorithmic, like any kind of algorithmic music recommendation system works, well, then you make a lot of money, right? Whether you're a publisher or whether you're an artist. And also the thing is, other music companies like competitors to Spotify, right? Like I don't know, Apple Music or Amazon or who else is out there? YouTube Music or what was Jay-Z's music system? Tidal, yeah. So again, these smaller companies, they try to figure out how these recommender systems work, because this is what makes Spotify very successful, because they're very good at recommending things that you might like, right? So again, they give you brief hints of how these things work, like what they use, what is their inputs. So what time of day you listen to, what kind of tempo is the music that you listen to is, languages, length of song, genres, musical elements. Like they tell you like these are the things that they use, and most of these are obvious, but they don't tell you how they use them. So we have to look at the results. This is a kind of a black box. We have to look at the results, and then we have to figure out, okay, what is this recommendation system using, right? And they filter out things that they think is not profitable to you. And so the way to discover this kind of thing is generally to create like blank accounts, like new accounts, new Spotify accounts, and then listen to sets of songs so that you can create associations between them. And then you listen to groups of songs together. I mean, you don't listen to them. You run Spotify with like a bunch of different songs linked together. So you figure out co-occurrences. You figure out which songs are associated with what, and then you see what is Spotify recommending it to you after you have listened to this particular genre or this particular tempo of song. And that's how you end up figuring out how these Discover Weekly things work, how these algorithms, what is this algorithm based on, right? Um, they have given us, like, there have been research papers which talk about how this Discover Weekly loop works. So they essentially they group users together into customers, just as like big box stores do, right? They group like all these Costco or HEB or whatever. They group certain types and profiles of customers together, and then they market to those targets. Right? Spotify does the same thing, because that's how you make money. That's how you know that you're not wasting resources, whether it's like computational resources in Spotify's case, or actual physical resources in the case of a big box store. And in some of these ways, you don't want the customer to decide like, okay, am I liking this or am I not liking this? What you want is the customer to use something, right? To buy an object, to listen to a song. That's why any kind of interaction with an item is considered like positive interaction, because that's how you create co-occurrences in a prior analysis. So it doesn't matter if you liked or hated a song, right? It matters whether you listen to it, whether you upvoted or downvoted a video doesn't matter. What matters is that you interacted with it. And that's how profiles are built. That's how you build these association rules, and that's how you end up recommending stuff to people, right? Now, obviously, the prior analysis that we're going to do today is fairly basic, right? We're not going to go into matrix factorization. We're not going to go into RNN-based methods, which all these people use. But the fundamental principle is the same. So what they do is, like I said here, their actual algorithm is kind of a matrix factorization-based approach, which has this transaction database of like user one, and they have listened to these artists. User one has listened to these particular songs, et cetera, for user one, and then they group them together. So user one has a list of artists, user two has a list of artists, user three has a list of artists. And so they do this kind of decompression where they do is they look for factors that are not just like artist names or band names or music names of the songs themselves. They also look for more varied factors, right? Like the tempo, like how long each songs are, what is the genre, and things like that. The next slide is going to show you what are the things that the abstract latent factors that Spotify classifies, right? So these are the things Spotify looks at. So this is kind of old. This is from 2014. So in this last 10 years, Spotify has in all probability increased this by like a factor of 10. So there's probably like 400 or like 100 different rules that they look at. But what they do is they look at these factors: acousticness, danceability, energy, instrumentalness, liveliness, loudness, speechiness, tempo, and balance. It's from 2014. I have no idea what half of these things mean, but what it essentially means in the case of Spotify is that uh, I'll talk about what a priori analysis, how this works, but what you want to understand is like what they do is something like the example that you've thrown over there, right? Like if a certain percentage of playlists of a certain class of users contains Arctic Monkeys, they also include the band Strokes. So that is an association rule, right? You don't have to understand anything more about that group of people other than that this association works. That this is like an actual association between a certain group of people. You don't need to know anything more about it, right? And then that is through playlists, and then you can do it by genres, right? So users who listen to indie rock and jazz have a 80% probability of enjoying neo soul. I don't know what neo soul is, but that's the kind of rules that get generated by genre. And then you do this for all of these things. You do this for acousticness, you do this for danceability. And so you have a big set of rules, and you have a big group of like lots of groups of users. Like, and each of those groups of users follow some of these association rules. And if you follow the rules along, then you can guess whether any given user, what any given user is going to prefer. Right. So you take a particular profile of user and you follow all of these rules along, like these example rules that are written here, and then you follow them through, and then your recommendation system, that your final recommendation, that a person who has liked all this kind of stuff is going to like this thing, is going to be more and more accurate, and that's how Spotify works, and that's how Spotify's recommendation system is considered super powerful. On the other hand, Netflix does the exact same thing. Yeah. Netflix very specifically says that in their papers, even though a lot of this never comes out. Like neither Netflix nor Spotify publishes their recommendation system because that is their IP, right? That is what the core of their business is. So they're not going to tell you how they do it unless you join, and then they're going to tell you. So like it's kind of like the secret sauce, right? So, but Netflix specifically tells you they use a form of associated hook. They use it for content recommendation. They use it for other things. They use it also for content creation. So they use association rules, mining, like much more complicated rules than what you're going to see in this class. But they use it to identify directors, to identify stories that they want to pursue, to identify like which markets they want to target and what kind of shows they want to produce. All of these, they use a form of association rule mining enhanced with like various kinds of machine learning and collaborative filtering techniques to do this kind of things. So something that users have noticed and something that Netflix themselves has seen is that they're very much one of the like most important things from someone like Netflix is sequential viewing behavior. So what are you, if you're watching a certain serial, if you're watching a certain TV series or whatever, what are you more likely to watch next? Like that is critical. So like we have talked about co-occurrences, we have talked about rule minings, and now we're talking about sequential behavior. So this is very critical to Netflix because it keeps people in their chair. It keeps people subscribed to their service. So things like after watching a particular series, after watching Stranger Things, a large majority of users also watch Dark within 2 weeks. So that kind of sequential mining rules, um, and well, they get much more fine-grained detail, like which part of the episodes do you usually stop watching? When do you usually skip forward? Like which parts of the episodes do you skip forward? All that kind of information is stored, and these rules are mined for more understanding of when to switch people, how to create their shows, like when do people get bored, and so on and so forth. You will find that, for example, Netflix has recently talked about this, but they started explaining things out loud within their shows. So when something is happening within a show, you will find that the actors themselves are more likely to say what they are doing, even if it is like clearly visible, because they guess that a certain group of viewers they look away from the Netflix screen, right, and they're like abstractly listening, and then they look back in and they don't know what's going on. So to avoid that, they started telling actors and directors to explain things out loud, to say what you are doing, what you are seeing on the screen out loud. So again, these are shorter rules that crop up when you study all exactly what's going on with everyone. Right. So now that we have done the examples, let's do some actual definitions of like association rules. Right. So these are the three things that are critical to rule mining. Right. For your problems, for your final rules or whatever. That is support, confidence, and lift. Right. So we um, these are essentially what are called interesting. Hang on, why is it not? So all these things they are called interestingness measures, right? Because what they do, or the support, confidence, and lift, is tell you out of your entire transaction database which transactions are the most interesting. So which transactions give you the most information out of the noise, right? That is the entire purpose of this kind of data mining, this kind of data science, is to filter the signal out of the noise, right? So this support, confidence, and lift, these three interesting measures, they are going to tell you which of these are uh, like which of these transactions can give you the most interesting results, right? So what does support mean? So if the probability of two things occurring together, if X implies Y, X is an event or X is a transaction within a database, and it has support S, if the probability of both of those things together is that value F, right? So it represents like how many of among all the transactions within the database. So there might be millions of transactions within the database, especially for something like Netflix or something like ACB. How many of those transactions contain these items together? That's what support means. Confidence means that uh, if you have a rule that buying X also leads to buying item Y, or watching item X also leads to watching item Y, what percentage of those transactions also contain all the items within Y? So if you have two groups of rules, so if you are buying, say, seeds and solar panels, solar lights, and your Y is the mulch and soil, then how many times do all the items in this group Y appear within this entire transaction database. And support of an item essentially means co-occurrence, right? If, uh, if these two items together, how many times do they occur? That's that's just what that's what support means. Right? So those are support, confidence, and lift. Yeah. Okay. All of these things together are if-then else statements, essentially. So they are logical statements. So if two items occur together, if two events are occurring together, then X event will also occur. So that's what you're trying to figure out. Like what is the probability of X event occurring, right? So if in this example, this is an example taken directly from the original market basket analysis. So you'll see a lot of apple and cheese and beer and all food stuff. Essentially, you'll see food stuff in a lot of these examples because they come from market basket analysis. So if you have a rule that say you have looked at the data and created a rule that if someone buys apple and cheese, then they also buy beer for some reason. So if you have a rule like this, then there are two things you can measure out of that rule, right? Given your entire data set. So if the first part of the rule is true, like the basket contains apples and cheese, then how many times is the second part also true, that the basket also contains beer, right? And this sounds like your machine learning accuracy, right? Like if there are two inputs coming together, how often are they hitting the exact output that you want, right? And what this is important for is that you want a confidence threshold. So whenever you're creating these rules, that when people watch these two things together, they're also likely to watch this third thing. You need to have some kind of threshold to cut off trivial rules. That like if people watch two advertisements together, they're also likely to watch something else. But if people are watching, I don't know, NCIS and The Office, then because almost everyone watches those, then if you say people who watch NCIS and The Office also watch, I don't know, some popular shows, Stranger Things. That's not a rule that's going to have a lot of support because well, everyone does it, right? And on the other hand, if you have like something very unique that a person who watches this very technical podcast and a person who watches this other legal podcast is also likely to watch some story-based podcast like Magnus Archives or something. Uh, Again, if these rules are too unique and these rules are they don't have enough support, then it's a waste of your time to follow these rules to the logical end. So that's why the confidence threshold, you'll find that whenever you have a association rule finding problem, you'll have to figure out, or it will be given to you in the problem itself, that okay, you find all the rules that support this rule, support this association above a certain confidence threshold. And sometimes you'll also get it below a certain confidence threshold. So there's going to be a band filter where your confidence rules findings are going to work. The way this works is it's kind of very simple. So confidence X to Y is support of X union Y divided by support of X. Lift is support of X and Y divided by support of X times support of Y. Again, support means how many times does this rule occur within the entire database? That's just basically support. And confidence of X to Y is the formula is given over there. Now, the other associated measure with a rule like this is support. So how many times, this is the trivial part, because how many times the database contains the F part, very easy to calculate. You look at the database and you can see how many times this initial part occurs. So, and you also generally have a support threshold as well, because again, you don't want the extremes. You have to cut out the extremes to make sure that your rules mining makes any sense whatsoever. So this is what a problem looks like. So given these interesting X measures, if you have in your basket A, B, and C, and you have these rules, so your support A to D occurs So that you see that there are 5 baskets, right? And how many times does A to D occur? It occurs here and it occurs here. So the support is 2 out of 5, right? And so on and so forth for all. And that's how these calculations are done, right? Frequency of xy divided by n, frequency of x and y. So frequency of x. So A to D is 2 out of 5, but the confidence, how many times does A occur? A occurs thrice in these 3 baskets. So your confidence is 2 out of 3. And then lift is the support divided by support of x times support of y. Okay, this is very simple. As long as you keep this particular formula in mind, you can calculate all 3 interestingness measures. What do we do with this interestingness measures now that we know these are things? So what we have to figure out is what are the frequent item sets? Like, so what are the groupings? What are the co-occurrences that occur more than usual, shall we say? Right. So these are again examples. So unusual things that are unusual that work together. I remember a story like from like some 20 years ago from like Walmart or Costco or one of those big shops, is that they were very they were very easily able to predict when women were pregnant because of the things that they were starting to buy. So if they were buying certain, like not just like maternal products, but also related products, and they were able to judge even before like people in the family knew, they were able to guess when someone in that family was pregnant, which led to lawsuits because you're figuring out stuff that people don't want figured out. So again, all these rules, all these big companies, and that's why none of these rules are open to the public, because they're usually very unflattering, right? They tell you things about people which people generally don't want to know about themselves. So uh, a lot of these unusual things that work together, these are what you want to figure out. This is the target of this kind of association rule mining. Is you want to figure out like what are the frequent item sets? Which items are related to each other more often than they are not related to each other. These are some examples. So in the market basket case, that's how they split these things together. So they have a large set of items essentially, and then they have a set of baskets. So baskets are what people are using, right? Which is a subset of the original items. And what you want is connection between these items, not between different baskets. Because different baskets are considered independent of each other. Well, there are higher order rule minings where you can see that, okay, during certain seasons, groups of people tend to buy some things together. But in general, what you want to do is you want to figure out inter-basket, like what is the relationship between items within a basket, rather than you comparing different baskets together, right? So this is an example straight from the original market basket analysis paper. So this is what transactions look like, right? So someone has bought apple, beer, whatever the third thing is, rice, and chicken, and so you have transactions that work together like this, and you take groups of these transactions, and then you figure out support of each of them. So say for example you want to figure out the support for, is that a tomato or an apple? That's a tomato, right? Yeah, apple. Okay, I'll say it's an apple. So you figure out the support of an apple. So the apple occurs 4 times out of these 8 transactions. So the support is 4/8. So then you do confidence using the same formula. So how likely are you to buy beer if you have already bought apples? So for that the formula is support of apple and beer divided by support of apple. And for lift, it is support of how likely is it that you have bought beer when you have already bought apples. So the same question, but answered in 2 different ways, right? So you want to figure out if you buy Apple, what are the odds that you also buy beer? And then you also want to figure out if you have bought beer, what are the odds that you've already bought apples? Right. So you look forward and backwards. If you don't do both these things together, you're more likely to be biased in one direction or the other, which creates problems. So if the so these are some things that you need to know. If the lift is one, then that means there is like no association between the two, right? If the lift value is greater than one, then that means the beer in this case is more likely to be bought if Apple has already been bought. And if it is less than one, then that means the rules are reversed. So like it is less likely to be bought, right? So you can already imagine how you would use something like this, right? You would put associated things together in a big box store, right? You put aisles together like this. Or if you're trying to be clever, you would split up like associated aisles by putting something that is not associated with them in between them. So when people are moving through the aisles buying X and Y items, they also buy whatever is in between X and Y. So now, if you look at all these possible combinations, it forms a tree like this, right? And so initially you have not bought anything. A, B, C, D, and E are individual items. And all possible combinations of these items, like two-level combinations, three-level combinations, four-level combinations, five-level combinations, are your possible item sets. And what you're going to do in using association rule mining is that you're going to prune this tree to keep only the frequent item sets left behind you. So then you're able to follow. So if you're able to prune this tree and remove half of these things, then you're able to follow that chain of causal associations all the way to the end. So you know what is the order of things that people buy in and what is most likely that people are going to buy if people have bought one item together. Now the thing is, in the real world, you won't have 5 items. You're gonna have like 500,000 items. So the tree is going to be huge. It's going to be like the complexity of this is going to be like exponential, right? So there are 2 to the power of I minus 1 candidate item sets. And even for 5, this becomes like unwieldy. So you can imagine for 500,000, how complicated it becomes, right? So that's why we prune it. We prune it very, very, very aggressively. We prune it using support confidence thresholds. We prune it using frequent item sets, but that we prune this tree to give us something that we can use to sell our products. That's the end of it. So this is what the a priori analysis does, is that it takes a tree like this, and then it cuts off keeps the frequent item sets. It cuts off infrequent item sets, and it keeps a smaller subsection of the tree. And that tree is our eventual things. So what a priori analysis does, what you're going to see, what it does, is that it does a breadth first search, right? This is kind of useful because if you are doing if you are not doing a breadth first search, if you're going straight down, and if the item sets, even if it was more than 5, if it was 500,000, then you'd be spending forever for your first traversal, right? So the breadth first search keeps us more confined to what is more interesting to us right now, and we're able to calculate the interestingness measures step by step instead of calculating like huge values of interestingness measures, which we might never end up eating. Also, a good thing about breadth first search is that if you are pruning a tree, it's very easy to cut off entire subsections of the tree very quickly, right? Because even right from the start, if you're cutting off like three of these elements, then you're cutting off 60% of the tree immediately. So the entire solution space that you have to traverse gets shrunk very fast and very quickly. So this is how it works. You take the candidates of dimension 1, then you compute the supports of all the candidates of dimension 1, right? So the support formula that you already know, you use that. Then you continue doing this. You generate the candidates of dimension 2, you compute the support, and then whichever one doesn't falls below your support threshold, you cut that off, right? and then you progress. So you can see that the tree has already become much smaller just because you have cut off this one thing. So the tree becomes much smaller. And then when you keep on pruning it, you go further down the line, uh, you find another one that doesn't occur in your transaction database that falls below your support threshold, and it gets pruned again. And so your final result in frequent item set is this one, right? So this is what you are going. This is what you will be doing essentially. So the algorithm, the flowchart is very simple. You're given item sets. You generate these individual, like all possible combinations of these item sets. Like so, if you're given A, B, C, D, E, you generate all the possible combinations of them, and then you check for support at each level. You prune anything that falls below that support level, and you continue this step until your frequent item set is null. It's very simple. It's not very complicated. It's just you have to keep that in mind that you have to check all possible combinations. That's a big thing. So, well, a big advantage of this is like this is very simple, very easy to understand. Right? The entire API principle is very easy to understand. If you have what if you're more likely to do X and Y things, and that implies you have also done Z things, that's how you prune the entire database. That's how you prune the entire frequent item set list. So, and the join and prune data sets steps are very easy to implement in large databases because this is a very like the graphs, while they are fairly deep, they're also very wide, and those kinds of graphs are very easy to implement and very easy to optimize for within modern databases. Like a modern PostgreSQL database is going to like if you have like a million data points in that, so 2 to the power of 1 million minus one nodes in the graph, Postgres is going to handle that within minutes. That's how optimized these modern databases are. But the problem is, even though this transaction is pretty fast, the computation required, because you're computing so many supports and then you're doing this comparison, it is kind of slow. There are optimization methods where you pre-compute a bunch of support values so that you don't have to like do the support calculation over and over again as you go deeper into the breadth first search. You might have done this during in your algorithms class, but is that every time you do this computation, it doesn't go get much smaller. You still have to do a lot of computation, and essentially, despite the pruning, you pretty much traverse the entire database at least once. Because at the outset, the first time you run this, you don't know what are the frequent items that you don't know what your support level should be like. So you're traversing the entire database at least once. And if you're doing this for, say, for example, for a big box store or for Netflix or Spotify or whatever, there are new songs constantly coming in. So there are new users constantly coming. People are constantly publishing. So your graph is not static. The graph is like constantly changing, constantly working on it. It's a complicated thing to handle. So where is it used? It's used everywhere. Recommended systems are used everywhere. Um, in modern cases, if you have all of you know of LLMs, right? LLMs in general are an association rule, like very broadly, uh, because what they do is they predict the next token in a sequence. That's how large language models works. That's how like ChatGPT or Claude or Gemini or whatever works. Given a set of tokens, they predict the next token in line. So it's not as Markov as that sounds. Like obviously there are much more complicated things going on behind, but in general, if you want to be very clear, if you want to be very simple about it, you can model an entire LLM, even a complicated one like ChatGPT or Gemini or whatever. We can model it as a set of association rules that the LLM is following. And it's used in multiple different cases and used anyway, like any system that you can think of where a recommendation might be needed, it's almost guaranteed they're using some version of a priori analysis. So what are so how does frequent item sets work? So you have a list of all items. Then you have in the graph itself all the items that have been considered frequent. Then you do it again. Then you consider like which items are frequent from that initial list of frequent item sets. So you keep pruning it. So this is a mathematical representation of the graph that you saw. So you have the first level, which is all items, and then you prune it to all the items that are frequent. Then you check for frequencies within that level, and so on and so forth. It's just a re-up of that graph itself. So, what is the a priori principle? I mean, I've talked about this already. So, if an item set is frequent, then it's all of its subsets must also be frequent. So that is the critical a priori principle, right? And if an item set is not frequent, then all of its supersets cannot be frequent. So the support of an item set never exceeds the support of its subsets, known as anti-monochrome property. So what this means is that in any case, when you have certain groups of things, like certain things that people are buying together, if that is frequent, then any smaller part of that set of items would also be frequent, right? So if there are 4 items that people always buy together, like going back to the soil example, if people are always buying seeds and I don't know, solar lights and mulch and soil together, you have seen that that item set is frequent, these 4 things. Then any subset of those 2 things are also going to be things that people would buy more and more often, right? So that you take that principle in reverse, and then you can figure out which individual items are the most frequent, and then you follow that all the way down into which groups of items are most frequent. So what the a priori principle tells you is that any item set that you find that is more than null, if it is frequent, then any subset of it that you can make is also frequent. And if an item set is not frequent, that it is not occurring enough times that it doesn't fall above the support threshold, then any of its superset, then all of its supersets, so all the possible combinations like of the items that it came from, all of them cannot be frequent. There must be some infrequent item sets within its superset. And obviously, if those 2 things are true, obviously the third thing has to be true, is that the support of an item set cannot exceed the support of its subset. So you cannot have an item set occurring more often than any of its individual subset items. That's obvious. That's by basic mathematical principles. So how do you do this? How do you do this manually, right? So you're given an item, you're given a count, then you create pairs out of those, so you are given something like this, TID. That's what you will be given in your exam, in any kind of problem solving thing. So that's what you'll be given. Then you calculate this thing, right? Calculate how many times bread has occurred, Coke has occurred, milk, beer, diapers, how many times in the occurred, and then given that the minimum support threshold is 3, so you drop Coke and eggs. Then you take all possible combinations of everything. So bread, milk, beer, and diaper. You take all the 2 items and combinations of them, and then you see how many times they occur here. So bread and milk occurs 3 times, and so on and so forth. So anything that's below 3, you trim. So then you take all possible combinations of the remaining items, right? For bread, milk, and diaper. So how many times can you combine all the items that are remaining? Well, you can combine them in only one way, and the count is 2. So this falls below the support threshold of 3, and so it's dropped. So it is below the minimum subset of 3. So it has to be dropped. And this uses the a priori principle because bread, milk, and diaper. Bread has a minimum support of 4. Milk has a minimum support of 4, and diaper has a minimum support of again 4. So using the a priori principle, this is the only triplet that you can form out of them, and the count threshold of this is 2. So again, this is also dropped. So this is let's do this slowly. Okay, let's say this is the database that you have been given. Generally, I would prefer, this is in numbers, but I would usually prefer, no matter what's given, convert them into alphabets like A, B, C, D, or E. Makes it much easier. You don't confuse yourself by calculating the support and threshold of numbers, right? So you take this, then you scan the database. So how many times does one, how many times does two, how many times does three, how many times does four, all of these things occur, right? So this is the first item set. The support of each of those item sets you can see here. Now you calculate the minimum support threshold is 2, so you drop 4, and then you have 1, 2, 3, and 5, which have more than one minimum support. Then you combine the frequent item sets of this out of 1, 2, 3, and 5. So these are the frequent item sets. So how many times do each of them occur in this original data set? Well, you can. This is how many times they occur. Like how many times does 1 and 2 occur? So it occurs only once. How many times does 1 and 3 occur? Well, it occurs twice because it occurs on item TID 100 and it also occurs on item TID 300. Remember, they don't have to be sequential. They just have to occur, right? You're not worried about sequential. So this is the item set that is created. Then again, you drop 1 and 2 and 1 and 5, right? And so these are the remaining item sets: 1, 3, 2, 3, 2, 5, and 3, 5. And then using the Apriori principle, the only frequent item set that you can create out of them is 2, 3, and 5. And how many times is 2, 3, and 5 occur? It occurs twice out of them. Because again, remember, how are you creating this? You're creating this by creating all possible combinations of these things, right? So you combine 1, 3, and 2, 3, you get 1, 2, 3. Combine 1, 3, and 2, 5, you get 1, 2, 3, 5. That's too big. You combine 2, 3, and 2, 5, you get 2, 3, and 5, right? And that is above this threshold. So that's how it works. That's how it proceeds. And then you have an item set 2, 3, 5, and the support is 2, and with minimum support 2. So what is candidate? What are the list of items? You have this. So this is how this entire process is done. It's not very complicated. You just have to be thorough that you're not missing anything at any point. So this is how this entire association generation rule mining process works. Initialize, you generate one item sets. Then you create the candidates, you prune the candidates, you calculate support, identify frequency. Then you check whether it has reached any kind of termination condition. Then you generate the association rules and then you interpret it. So, what the frequent item set generation, we have already seen how that does. Now the next part is rule generation. So you have to generate like high confidence rules from each frequent item set. So you have a left hand side and a right hand side. So if you have a frequent item set like ABCD, in this case 2, 3, 5, or in the previous example it was bread milk diaper. So if you have a frequent item set like that, then you can create a rule like AB to CD, right? Because how many rules can you possibly create from here? Take a pick. You can create from A to BCD, from B to ACD, from C to ABD, from D to ABC. Then from AB to CD, from BC to AD, and so on and so forth. You get what I'm saying, right? You can create lots and lots of different rules. But which of these rules are strong? So the way to check if all these possible rules, 2 to the power of I minus 1 rules that you take, if they are strong, is that if the support of these rules is greater than the minimum support and greater than or equal to the minimum support, and if their confidence is greater than or equal to the minimum confidence, right? So that's what you're doing. So for that bread, milk, and diaper thing, so your minimum support is, say, you have been given that the minimum support is 0.3 and minimum confidence is 0.6, and you have found that the support is 0.4. So it's greater than this. So it stays. So now you all look at all these possible candidate rules, right? And these, and then you for all of them, you calculate this thing. But any of them that fall below this minimum confidence threshold of 0.6, which means these two rules fall out of it, these are the rules that stay, right? Out of bread, milk, and diaper. So you have to create all possible rules. Then you have to calculate the support and confidence for all of it. This can be kind of slow, but the values that we give you in your exams are, are mostly made so that this calculation is very fast. Like there's only going to be like 4 items, 4 or 5 items, and you can do this calculation on your head. So this is how rules are calculated. And then once you have these rules, you once you have calculated the support and confidence, you know that according to the Apriori principle, any subset of a frequent item set must be frequent. So if ABC is a frequent item set, so the end process of your initial rule mining is giving you this kind of frequent item set. Then you generate all possible candidate rules out of ABC. Then you select rules with some confidence, right? This is it. This is what all that is saying, right? So again, this is just restating the point. If you have a frequent item set A, B, C, D, then you have all these possible candidate rules, and you have to check the support and confidence for all of them, and then you drop any that falls below that rule. So what happens is that if you have the frequent item set graph like this, you prune out a bunch of these rules that don't fall under this minimum confidence threshold. And because you know of the prior principle, if you cut out one of these things, you can be sure that anything that's downstream of it can also be safely pruned and is not going to be frequent. So a minimum, some of the factors that deal with this is that your choice of minimum threshold is very hard to get a good minimum threshold without doing this whole thing once. Like we are giving you a value in your exams, but in real life, you're going to have to do this once at least to figure out what kind of minimum support threshold rules that you might need. Okay, these are the size of the database is important. The average transaction width is important. Dimensionality, that is the number of items, is important, and so on and so forth. Okay, so now like the class is over, but we have a in-class assignment after this. So what you just saw, we're going to do this. I mean, you are going to do this on this user list. This is a Spotify user listing habit. So you're going to find the frequent item sets with the support threshold of 2, so it has to occur twice. And you're going to generate association rules from that frequent item set whose confidence is greater than 0.75, so 3 out of 4. The first thing you should do is you don't want to calculate these big names, right? So convert them into A's and B's, or convert them into 1 and 2. So Taylor Swift convert her to T. Olivia Rodrigo convert her to O, and so on and so forth, right? So to make the entire calculation easier. So take a photo of this or write this down, and then we are going to go through how to do this. This is the last thing we're going to do. So you have to submit it. You'll find on Canvas, there's an in-class Apriori assignment. Whatever results you get, you submit it over there. Okay, it's going to be open till 6:30, so you don't have to rush to do it right now. But this is what we are going to be doing. Again, note this down and convert it to something that's easier for you to calculate. Whether it's just ABC or whether it's just PO, OR, DP, MTS, whatever works for you. So the first thing to do is find the frequent item sets, right? With support of 2. So once you have this list, the first thing you're going to have to do is find the frequent items. Okay, has everyone noted this down? This particular image. So I'll go back to how to do this. Okay. If anyone's still copying this down, let me know. Okay. So the way to do this is essentially this, right? This is what you are going to be doing. So you're going to so in this case, items are labeled like 1, 3, 4, but in your case, those you can label them however you want, right? So you're going to scan the user ID database, and then you're going to find the support for each of them, for each of the individual items.
Just because the threshold has to be, since that those two, you have to be 2 or more.
Yes. So you have to create. So I think it's mentioned in the question. It's greater than or. Yeah, it says equals to 2. If it was greater than 2, then you would look for threshold that is above 2. But here it's equal to 2. So this is essentially what you're doing. Taking individual artists, then you're finding their support, then you're dropping anyone whose support is less than 2, which in this case I think would be dark font, whatever you have labeled. then you keep doing this. And whatever artist is left, then you create all possible combination of those artists. Like this, then you scan it, you do this, and then you create this, then you create these out of like three item sets out of whatever is there. Then you check the support for that and publish it.